Okay, in this video, we're going to talk about Lenz's law. Earlier, in the previous video, we talked about Faraday's law. And Faraday's law, let's just do a very quick review, told us how to get the magnitude of an induced EMF. An induced EMF is the absolute value of the time rate of change of the magnetic flux. Now, if we happen to have more than one loop, then we'll need to multiply that by n, where n is the number of loops. And we also want to keep in mind that when the flux is changing, you have several possibilities. You may have a situation where the actual magnetic field strength is changing, so it's either increasing or decreasing so many Tesla. You may have a situation where the actual area of the loop is changing. The loop could be getting smaller or larger, or you could have a situation where the angle was changing, and as a result, you're going to have a change in cosine values. But this is all Faraday's law, okay? Just want that to be kind of fresh on your mind. Another thing that we want to review before we start are our right-hand rules. Now, the very first right-hand rule that we got, we're going to go over 3 of them, and really only 2 did we dwell on. One is the force on a positive charge or a conventional current. Let's assume that we have a magnetic field that is directed into the board. So we draw X's showing that B is going into the board. If we have a positive charge, let's let it be traveling this way. Then to determine the direction of force, I would take my right hand, I would put my fingers such that, here they are, there's my pinky, there's my fingers, such that I could curl them towards the magnetic field. And in order to do that, my thumb would have to be pointing down. If my thumb of my right hand is pointing down, then I can curl that into a fist so that my fingers rotate into the board like a magnetic field. If I had a conductor and it had a positive current in this direction, I would now have to put my fingers pointing to the right, which means my thumb would actually be pointing upward in order that I can take my fingers and I'll be able to rotate them, into the board this way. Now my fist would look like this. So in this case, we know the force would be up on that conventional current, and in this case, the force would be down. Obviously, if we have a negative charge, that changes the direction. But that was the very first right-hand rule we learned. Our second right-hand rule is about the magnetic field of a wire, a long, straight conductor. In that case, if we have a conductor, let's let the current go this way. We just grab it with our right hand. So in this case, if I take my right hand, with my thumb pointing in the direction of the current. So there's my thumb. My fingers are actually going to be like this. When I curl them around. So let's see if I can, that will actually kind of, erase more than I wanted to there. But you can see my hand would actually grab, there's my fingers, like this. So I know that when I draw my magnetic field lines, they go in the direction of my fingers, like this. They form those concentric circles this direction. Those are the two that we really focused on. There is a third one that's going to be very important towards this lesson for Lenz's law. The third one deals with the magnetic field of a loop. And it's kind of an extension of that number 2 one. But what happens is, suppose that we have a current in a loop. Let's go ahead and draw a little bit of depth. It's a piece of wire. And the current is coming this way. How do I determine the direction of the magnetic field? One way is you could picture yourself grabbing that loop. If you grab that loop with your right hand, you'll see that the dots are on the inside, which in the dots, that's where it's strongest. That means the magnetic field would be pointing up, the way I've drawn it. But the other way is you curl your fingers with the loop. So if I picture curling my fingers with the loop, my thumb would point up. Here's me curling my fingers. Why does my art look so much better in my notes? But in order to curl them this way, that tells me that my magnetic field here points straight up. There's the value of V. Similarly, if I had a loop, and I'm trying to draw this loop where it's somewhat horizontal, and I reverse that current, so now the current is going this way. In order to curl my fingers with it this time, I would have to curl them this way, and my thumb would be pointing down. That tells me the magnetic field points straight down. So picture your fingers going in the direction of the current, and your thumb will point in the direction of the magnetic field. Okay, this is the one we're going to need when we use Lenz's law. So what does Lenz's law say? The direction of any magnetically induced current or EMF is such as to oppose the direction of the phenomenon. And I'm going to tell you right in there, that probably means very little to you. Lenz's law says the induced current will always, and the opposition part is important, oppose the change in flux. That's really what it means. The induced magnetic field, because remember, if you induce a current, you're going to induce a magnetic field, always opposes the change in the magnetic flux. Another way of thinking about it is it tries to maintain the status quo. I don't think that's going to mean a lot to you either until you really see me work some examples. So let's look at the different possible cases. So case number one, if the flux through a loop is increasing, the induced magnetic field points in the opposite direction of the original magnetic field. To make this a little easier to understand, we're going to consider the original, we're going to label some things. The original magnetic field I'm going to call B0 for original or BO, and the induced I'm going to call BI. So we know one of them was the original, one of them's induced. So let's suppose I have a current loop. And I tell you that the original magnetic field points up and is increasing. That means this magnetic field starts out pointing up and it's getting bigger. Remember, you won't have a current unless there's a change, but there's a change in current magnetic field through this loop. That will induce a current. That means, and I'm going to draw this one in a totally different color, that BI will point down. Now I want to be very clear. It doesn't point down because the original magnetic field points up. It points down because the change in B is up. Right? That means the change in the original is up. Therefore, the induced will point down. So if I want an induced magnetic field to point down, I want this one. Wait, that's not even the color I wanted. I really wanted this color. I want this one to point down. So what direction will the current go? Well, take your right hand, point your thumb straight down, and you can see that the current must go this way. I is clockwise when viewed from above. do another example. Let's take a loop. There's our current loop. And let's go ahead and say that B0 points up just like before and is decreasing. That tells me that the change in my original magnetic field is down. If I was going to draw this, I would say, look, there's a magnetic field that points up, but it's getting smaller. It's coming down this way. If the change is down, then my induced field has to be up because my induced field is trying to maintain the status quo. So if the change is down, the induced field will be up. BI will therefore points up. If BI points up, that means my thumb has to point up. So I take my right hand, my thumb points up, and I can picture the current will come around like this. That means I is counterclockwise when viewed from above. Now you have to read problems, whether you're viewing from above or viewing from the left, but from the point of view that you're looking down on the situation, I will be counterclockwise. Okay, let's try a couple more. What if the original points down and is increasing? That means the change is also down, just like it was in the problem above. If we picture that, there's a magnetic field pointing down and the change is down. Okay, that means the induced field points up because it opposes the change. It doesn't oppose the original field, it opposes the change. So there's BI. If my thumb points up and I circle my hands, I see the current does this. I is counterclockwise. Will you see CW when viewed from above? Notice it's the same result as what we had in the problem right above it. In both cases, the change had to point up because in both change, the original one, the change in B0 was pointing down. Let's do one that's not. Let's look at some more possibilities. What if we have one like this? If I tell you that the original magnetic field points left and is decreasing, that means the change in that original field is to the right. So if I drew that, here's the original magnetic field, it points to the left, but it's decreasing, so our change is in the opposite direction. That means my induced field, BI, points left. It's trying to counteract that change and maintain the status quo. So if I take my right hand and I point my thumb, I can see how the current will flow. If I view it from the left, so you picture looking at it, looking straight at your thumb, if you're viewing it from the left, here's what my hand looks like. If I put my thumb out this way, my fingers have to curl like that. Not my best thumb, but you can see that when viewed from the left, I is counterclockwise when viewed from the left. Now, if they said view it from the right, I will be clockwise when viewed from the right. Okay, so that's Lenz's law. That induced magnetic field tries to maintain the status quo. If the flux is increasing, either because the magnetic field is increasing or because the area is increasing, we're going to look at examples where the area, if the flux is increasing in a particular direction, then your induced field will be in the opposite direction. However, if your flux is decreasing in a particular direction, then your induced field will be in the same direction as the original because it will try to shore it up to maintain that status quo. So let's look at least one example. Not actually have any numbers with this example. We just have kind of a directional situation. It's that slide wire generator again. We've got this magnetic field, nice and uniform, points into the board. I'm not going to draw a whole lot of it. And we've got this U-shaped rails. And on top of that, we have a conducting rod that's free to move. And it's moving this way. Okay, let's think about it. What will be the direction of the induced current? So if we pull that rod to the right, here's what we know. The original magnetic field is into the board. And increasing. Why is it increasing? The magnetic field is not increasing, but the flux is increasing. So maybe I should be careful there. Why is the flux increasing? Because the area is increasing. Okay, remember the magnetic flux is the product of the magnetic field strength times the area. And in this case, they're perpendicular, so it's really easy. So if the area is increasing, then the flux through the loop is increasing. So if V0 is into the board, that tells me, since it's increasing into the board, VI is out of the board. Take your right hand. If your thumb needs to point out of the board, the only way to have my thumb pointing out of the board is if the current is flowing this way. So your picture, your thumb sticks at your face, your fingers are curling. So BI is counterclockwise. Not BI, that's not what I meant to say. The induced current. Okay. So By pulling that conducting rod to the right, we're increasing the area. That means the flux through the loop is increasing. Since the flux through the loop is increasing, our induced magnetic field has to point in the opposite direction, which will be out of the board. So our induced current has to be counterclockwise. Okay. One more idea that we want to cover in this video that's very closely related to Lenz's law and what we've just done. Kind of puts it all together in a way. That's the idea. This is section 21.5, and it deals with motional EMF. An EMF that's due to motion. If you look at the previous problem, if we're inducing a current, we know that there has to be an EMF. Okay, so we're going to look at what that EMF would be. So we're going to start by consider, which just means let's stop and think about, a conducting rod moving to the right in a uniform magnetic field directed into the page. So, here's our conducting rod, just a piece of metal. I'm going to label this top end A, this bottom end B. It's going to be moving directly to the right, and our magnetic field points into the board. Okay, so it's moving with a velocity v, and at some later point, it's going to be over here. Just going to kind of draw it'll be here in a minute. Let's think about what happens to a positive charge inside this rod as you pull. So picture this positive charge right there. Or even better, let's picture the negative charges, because we know that in a metal, I'm going to have to erase just a tiny bit. We know in a metal, it's actually the electrons that are free to move. So let's just assume we've got negative charge. Think about a negative charge right here. If we use our first right-hand rule, if I put my fingers in the right hand in the direction of V, and I curl my fingers into the page, my thumb points up, that tells me a positive charge would feel an upward force, and that my negative charge would feel a downward force. All of the negative charges inside this rod that are free to move will feel a downward force. And so after a minute or two, this end will be negatively charged. As a result of these missing charges, this end will become positively charged. Okay, so a positive charge, Q, in the rod will feel a force, a magnetic force that's equal to QVB, and that force would be upward. Of course, the positive charges are usually not actually free to move. A negative charge, call that negative Q, in the rod will feel a force also equal to QVB, but it will feel it downward towards point B. Now, if you keep moving this, how long will those charges keep moving? Well, what's going to happen is as these negative charges accumulate at the bottom, making one end positive and one end negative, you're going to create an electric field. So the charges will continue to move until the electric force is equal to the magnetic force. Now the electric force is QE, and that has to equal QVB. That's the magnetic force. Notice it doesn't actually depend on that. And the electric field in this rod, if you think about it, is the potential difference from point A to point B divided by the length of the rod. That's going to give us our units. Remember, electric fields are volts per meter. So our electric field is the voltage difference between point A and point B divided by the length of the rod. So if I have the voltage difference between point A and point B divided by the length is equal to V. This is lowercase v. This is the speed vector right there, times B. What I see is the voltage difference between the 2 points is equal to VBL. And that's our formula for motional EMF, or an induced EMF due to motion. Motional EMF, E is equal to VBL. V is the velocity. B is the magnetic field strength. And L is the length of the rod, or the conductor. Now, we have to be careful because the motion needs to be perpendicular. If, for example, you had a magnetic field that pointed this way, and you had the rod pointing this way but going like this, there would be no EMF induced. Why? Well, if you picture a positive charge, if V is parallel to B, there's no force. Remember, the force is equal to QVB sine phi. If phi is equal to 0, because there's no angle between V and B, this whole thing will equal 0. So if the direction of the motion is parallel to the magnetic field, we're not going to get an induced EMF. Now, there is another possibility. Notice this, the first picture I gave you gives you pretty much the maximum induced EMF. What if instead we keep the magnetic field, let's just draw it like this. What if I have the rod where it's not, the velocity is still perpendicular, but the rod points like this? and it's moving this way. What's going to happen by the time it reaches over here? And let's assume, will there be a potential difference between end A and end B? And the answer is no. What will, whoops, let me change back to the black. What will happen if it's moving this way is, again, this side will become slightly positively charged, and this side will become slightly negatively charged, because the forces, if you picture that charge right there, it's going to feel an upward force. But you're going to see it's going to be a much smaller induced EMF, because now the length would only be this small distance. There is no difference in potential from point A to point B. Okay. Let's do a problem. We're going to let this be our last problem for this video. So this example is 21.7. It should be in your textbook. Again, we're going to have a uniform magnetic field that points directly into the board. We're going to go back to that, oops, not the color I wanted. We're going to have a conductor, a U-shaped conductor, like conducting rails. I think we already did our railgun problem. Looks like this. I'm going to put a rod across. The length of that rod from one end to the other is L. But in this case, they give us some numbers. They tell us L is 0.10 meters. The speed is 2.5 meters per second. The resistance of the loop is 0.030 ohms. And the magnetic field strength is 0.60 Tesla into the page or the screen. Start off with finding the induced or the motional EMF. That's easy. The motional EMF is simply VL. So 2.5 meters per second times V is 0.60 Tesla and L is 0.10 meters. We put that in a calculator, comes out to be 0.15 volts. I think we did a problem earlier with this exact same information with a slightly different approach, where we took into account what is the changing area doing Faraday's law, and we got that same induced EMF, but this was much easier. What's the induced current? Well, we use Ohm's law. Ohm's law tells us V equals IR. So our current will be our voltage divided by our resistance. In this case, our voltage is our induced EMF. Our resistance was 0.030 ohms. And that comes out to be exactly 5 amps. The third question wants to know how much force is needed to keep the rod moving at a constant speed. Well, let's think about the force on the rod. We know if we use Lenz's law, let's use Lenz's law for a minute. If the area is increasing, then the flux through the loop is increasing. And we know that we get a current, do a blue current, that's going around in a circle like this. So if the increase, if I use my right hand rule, I need to go in the opposite direction. So if I want the induced B to be out of the board, let me do the induced B in purple like I was doing earlier. To oppose that increase into the board, then I know that the current goes this way. So think about that rod. If you have the charges going up, the positive conventional current going up and into the board, you can see there's a magnetic force this direction, an induced magnetic force. If you're going to keep this moving at a constant speed, you're going to need a force in the opposite direction to balance it. We can think of that as being an applied force. How hard am I going to have to pull? Well, if I'm moving at a constant speed, I need to pull exactly equal to that magnetically induced force. So how do I get a force on a conductor? I go back to that formula. The force on a conductor is equal to I L B. And in this case, our current was 5 amps. The length of that conductor or that conducting rod is 0.10 meters, and the strength of that magnetic field is 0.60 Tesla. So I can see that the induced magnetic field is 0.30 newtons. That's how hard I'm going to have to apply to move at a constant speed. Right, because if I want to move at a constant velocity, then my net force has to be 0. And I don't know why I put that as D. That's still C right there. All right, part D, one more question. What's the power? The mechanical power involved here. Well, remember, power is the rate of doing work, but we also said when something's moving, it can be the product of the force times the velocity. So in this case, 0.30 newtons times 2.5 meters per second. And our power is 0.75 watts. Okay, so that concludes the video over Lenz's law and motional EMF. We have one more. We're going to talk about eddy currents, and we're also going to talk about transformers in the next video.